So today we will discuss about how we can write a machine language or assembly language programs using any processor. So we will start with a question. Let's say write a program to do a particular task. And before we start writing it, we will learn all the fundamentals what is required to write a machine language program. Now, before we start taking a task of writing ALP program, let's understand that what is in the resources or the platform we have it on which we are writing the program. Any system you take it, basically you have one processor will be there. This processor, I'm just considering it can be microprocessor, MUPI, it can be microcontroller, or it can be DSP processor also. So any processor you take it, that way of writing ALP programs and machine language program development is the same. It's not going to change. So now I have taken a processor. Now what else is required to develop the program and make the program run on the processor? Any program we take it, basically the program comprises of two components. One is the program consists of set of instructions. Now, since we are writing the program in a machine level language, assume that we are starting writing the program using the instructions provided by the processor. The instructions will look like that: add, subtract, mul, like these type of instructions. These are called as ALP or machine level language instructions, which are supplied along with the processor. So whoever writes the program using these type of instructions, they will use an assembler to convert into a machine language or binary format, and that will be used for execution. By chance, if you are writing the program in a high level language, HLL, then whatever the statement you're going to write, C is equal to A plus B, like that, you are converting using a compiler into a assembly code, that is ALP code. So, and then you are converting into a machine language format. Ultimately, whatever the program you write in high level language or assembly language program, your program should be converted into what is called as object code or machine language code. So in this code, your instructions will look like 0, 1, 1, 0, 0, 0, 1, 1, like this. It look like that, all the instructions. Now, this is one component of a program. What else the program comprises of? A program is also comprised of what is called as data. So why we require a data in a program? We know that whenever we develop a program, you're going to process some data, maybe the marks of a student. So the data of an organization, these are all the data. So this data can be numbers. Sometimes it's a numbers, it's a signed numbers or unsigned numbers. Sometimes the data can be strings or characters. So all these things will form what is called as a program. So generally when we write a program in high level language, as and when required the data, we declare them in the beginning of a program. We start developing a program. We declare arrays, we declare the structures, we start writing the program, manipulate it. When we write the same program in assembly language, you have to take little more care. That means that I should be able to segregate my data and instructions properly. I should be able to take a decision where in the memory this data should sit, where my program should sit. That means that I should be able to specifically know the hardware infrastructure, that is the processor, memory, everything. Then only I can start writing a program. When you write in a high level language, you're not worried about all these things. So this is the one difference between high level language and an assembly language. Since I'm writing the program in a machine level language or assembly level language, I require to know the necessary hardware which is required along with the processor. Now, processor is capable of executing your instructions. Processor is not capable of storing your program. So I'm talking about a microprocessor. Even if I'm talking about the microcontroller, I'm talking about the processor core or IP core, what is present inside the controller. So core or the microprocessor do not have the storage inside where I can store my program. So naturally, whenever you purchase any processor or a controller, you require what is called as a memory. Any memory, whatever you purchase, if you connect that memory to the processor by using a set of lines, the memory is called as a main memory. If the memory is not connected to the processor directly through the set of lines, like a hard disk or a floppy disk or a USB drive, which has got the data and the programs, but the contents of that will not be fetched directly by the processor for execution. You have to bring them into the memory. That means that whatever all other storage formats we have it, so we call it a secondary storage. I can keep my program here, but at the time of execution, I have to bring the program into the main memory and then I have to execute it. So that is the difference between the main memory and the secondary memory. So processor can access the main memory, whereas processor indirectly accesses the secondary memory. So I have to bring in my program from secondary memory to the main memory for execution now. So now this is the place where I store my program. Maybe I'll store the program in the beginning, then I can store my data after the program. In the other way also possible. So I've stored this one. Now, after I store the program and the data, so then I will ask the processor to execute the instructions one by one. Whatever the instructions we are going to write inside the program, let's go into the little more details about that instruction now. Now, any instruction we take it, this instruction has a set, it is a set of bits in a binary format, 1 0 0 1 0 like that. This instruction consists of following information. One is it contains what operation we are going to do it. That is called popularly as an opcode. That is what operation, it's an addition, subtraction like that. And every instruction specifies certain operands. Operands means the data on which I'm operating it and the place where I'm storing my data. So if I take an example of an add instruction, if I say add some number, I'll take it, I'll explain this, add R0, R1 and R2, if I keep it like that, that means that I'm adding the contents of R0, contents of R1 and placing the answer in R2. That means that this instruction has got the meaning called what operation add is there, and these are all called as operands. So I can also say that add a comma location 1. That means that add the memory value what is present in the location called A to the location what is there in the memory, again add them and store the answer in the location 1. That means that both are memory locations here both are the registers. Now we'll come back here into the processor again. So processor will have what is called a set of registers will be present for every processor. These registers will be generally called by the name as R0 to R31 if there are 32 registers are there, R0 to R11 if 12 registers are there in a processor. So when we write a program in assembly language, I should be very clear one aspect, how many registers are present inside the process, what are the names of them I should note down. And again, if I am storing my program and the data in the memory, I should know that where is my program is stored and where is my data is stored. Now, so let's come back to the again instruction, how the instructions are represented in the memory. We'll go into little more details on that. Now, the processor, whatever I have, is connected to the memory. When we connect to the memory, it is connected by a set of 3 buses. The first bus we call as an address bus. So this address bus is a set of lines which carries an address from the processor. So the size of the address bus decides the size of the memory. So address bus decides the size of memory or the total capacity of the memory. Let's take, if I have 4 lines are there, only 4 lines are there. Now what are the possibilities the 4 lines can give it? 0 0 0. So then 0 0 0 1, it continues like that, 1 1 1. So how many combinations are possible? 16. That means that if the address bus has got 4 lines, it can take combination from 0 0 to 1 1. That means that 16 combinations it represents. That means that the memory can have 16 different locations. Each location will have a one unique address. A memory is basically what? Set of locations. Set of locations will be there in the memory. So the address bus decides the size of the memory. What are the general address bus sizes which are used in the commercially available chips? So we will start with the 2 to the power of 16, which is used for 8086. So 64 kilobytes was provided in the what is called as 8051, the first microcontroller which is released by the Intel. It has got only 64 kilobytes were there. Then they have released 8086, so which they provided 20. So 2 to the power of 20. So 2 to the power of 20 plus another 4 lines they provide, 2 to the power of 24, they totally 24 lines they provided is 16 megabytes. So 2 to the power of 20 is 1 megabyte. 2 to the power of 10 is 1 kilobyte. You can remember always like this. N is 1 kilobyte. 2 to the power of 20 is 1 megabyte. 2 to the power of 30 is 1 gigabyte. You can always remember like that. So the 16 megabytes is given by 8086, 286, 80386. This is the total capacity provided by, including the 80486. This is the capacity provided by these processor. So the 2 to the power of 20 was provided in 8086. They provide 8086. So that will be 1 megabyte, 1 megabyte. So the MS-DOS was released, was developed for 8086 based system. When the DOS from the Microsoft they released, they have a total capacity of 1 megabytes is there. In that 684 kilobytes they're given for application programs, 384. So it was reserved for some other memories like a video memory, hard disk bias and other things. In the 684K, they were MS-DOS operating system. The balance was available for application programs. So that was what was available in the first processor, the first PC. Then the latest, almost all the processor now, they provide minimum 32-bit address lines. So 32 means it is a 1 GB is 2 to the power 30, 31 is 2 GB, 32 is 4 GB. That is 4 gigabytes. 4 gigabytes is the total memory what is possible in most of the Pentium, all these machines are available. Now, so once I know that number of address lines are provided by the processor, I can always specify how much is the memory capacity. After we generate an address that is
মই ক্লাছত আছো, মই পিছত কৰি আছো, আমাৰ অনলাইন ক্লাছ চলি আছে। আৰে মই পিছত কৰি আছো, অনলাইন ক্লাছ চলি আছে। হেল্ল',
can you keep it in unmute or mute? Okay, am I audible? Yeah,
audible, sir.
Yeah, okay. So every processor has got set of address lines. From that, I can able to find out total capacity of my computer system. So if I take the simple case of, let's say, 4 address lines are there, 16 locations are there. So let us take that example. Now, first address is 0. The last address is 15. The processor I have taken for just for understanding sake, 4 lines are there. Address lines, 4 lines are there. So I will call the first address lines A0, second address lines A1, third A2, and the fourth is A3. So what is the size of my bus? 4 for understanding purpose. Now, these 4 address lines will comprise, these 4 address lines will constitute 2 to the power of 4. That means that 16 memory addresses are possible here. Now we always use so every address, whatever we refer, the question comes into picture. This address can contain how much of data? How much of data can contain? So whatever the data we have inside one location, that refers the data supported by one address. All the current process which is available in the market, they will be called as byte addressable. So what do you mean by byte addressable process? Mohan, screen repeat ಇದಾಗ್ತಾ ಇದೆ, refresh ಆಗ್ತಾ ಇದೆಯಾ?
Oh yes sir, refresh ಆಗ್ತಾ ಇದೆ.
Okay.
ಸರ್ ಒಂದ್ಸಲ ಕ್ಲೋಸ್ ಮಾಡಿ ಓಪನ್ ಮಾಡಿ ಸರ್.
Am I audible?
Yes, sir. Audible.
As I was specifying that any processor, if it generates an address, as I was for understanding the basic, I was explaining that there are 4 address lines are there. Let's say I'll call as A0, A1, A2, and A3, 4 address lines are there. Since 4 address lines are there, my memory capacity is 16 now. Because why? 2 to the power of 4 is 16. So now I have 16 addresses are there. I am writing 0 to 15. Now, if I say the address 0 contains how much of information? How many bits can be represented in one address? So this is a common question is required to, we have to address it whenever we have a memory which is connected to the processor. The whole industry, they follow what is called as byte addressability. So it's called as byte addressability. So what is the meaning of a byte addressability? Even though the latest processor is 64-bit, 128-bit is available, still they followed with a old convention to support the old traditional process of the system. So what does it mean byte addressability? That means that if the processor has 16 addresses, because 4 address lines are there, every address represents only 1 byte of information. That means that, so how many bits are there? 1 byte, that is 8 bits are there. So one address is always referred as 8 bits. This is the meaning we have to understand. If the latest processor provides 4 GB, that means that the processor supports a memory of 4 gigabytes, where each address is referred as what? 8 bits. Now, so let's come back to the another bus. Now we have understood the address bus. We also understood byte addressability. Now let us take the other address bus to understand the meaning of that thing. Now we have understood address bus. So which if, for example, if k is the number of address lines, the first address is 0, the last address is 2 to the power of k minus 1. For example, because 4 is there, 0, 2 to the power of 4, 16, minus 1, 15. Similarly, I written 0 to 2 to the power of k minus 1. Now, there is one more bus is there, which is very important for every processor, which decides what the word length of a processor. So what is the word length of a processor? This is a very commonly used system, or commonly used term with a processor. Whenever we talk about or when we purchase any processor, the first question I ask is, what is the word length of the processor? How do you define the word length of a processor? There are 2 ways we can define, or you can say 3 ways you can identify the word length. Number 1, find out the size of the registers what is present inside the processor. The processor will have a set of registers there. If all the registers of the size 32-bit, that means that word length of my processor is 32-bit. This is one way to find out. The second method, every processor has got what is called as ALU is available inside. So what is the use of an ALU? Which performs addition, subtraction, or multiplication of any 2 operands. If the size of the ALU is 32-bit, that in the sense it can able to add 2 32-bit number in a single clock cycle or in one operation, then I can call it's a 32-bit. Now, what is the third way of recognizing the word length? It is amount of data I can able to read from the processor to the memory, or I can transfer from the processor to the memory. So this is we call generally as a data bus. Data bus is a set of lines, a set of wires, which carries the information from the processor to the memory, and also I can read from the memory to the processor. If the size of this bus decides what is the word length of a processor. For example, if the data bus size is 32-bit, then I'll call the word length of this processor is 32-bit. For example, 8086 supported the data bus of 16 bits. That's why we call 8086 as a 16-bit processor. The 8051 microcontroller, from the first one from the Intel, it supported 8 bits data bus. That's why we call it an 8-bit processor. So this is one way to identify. Summarizing, I can identify the word length of a processor by the size of the register, or by the capacity of the ALU, or by the capacity of the data bus. Now, for all practical reasons, now in this class, we will assume that the size of the data bus is the word length. Now is a typical question we require to understand. If the word length, let us take example, let us consider word length is 32 bits. Now, word length is 32 bits. Now, so that means that I can read 32 bits at a time from the memory to the processor. But the each address of the processor will support only 8 bits. That means that it is not possible to read 32 bits from the memory in a single shot. Because why? One memory location, any moment of time, I can able to read from the memory. Even though the memory consists of so many bytes, I cannot read more than 1 byte at a time because the memory will respond for one address. There is no two address buses are there. Only one address bus is there. Whatever the address you place here, it will respond for that. That means that I can able to read one among the 2 to the power of k minus 1 locations. That is 1 byte I can read at a time. But what is the capacity of the data bus? The capacity is 32 bits. So I want to read 32 bits. I am capable of reading 32 bits, but my memory provides only one address 8 bits. That is why they use a concept called banking. Banking in the sense they put 4 chips. So each chip will provide 1 byte of data. That means that, so the first address, they will place it here. Second address, they will allocate to the second memory. Third address to the next memory location for this one. Then again, it starts. So 5, 6, 7, 8 like that. All this put together, they will organize as a one configuration. So this type of organizing the memory to support the existing word in the processor, we call it a banking. You would have seen that in a motherboards also they provide multiple banks. They say that you have to close the 4 banks to make it work. So what is the concept? Why the concept of banking has come into picture? Because data bus, the word length is more than the amount of data provided by one address of that. By putting those chips, we call it the bank 1. So bank 0, bank 1, bank 2, bank 3. If I generate one address, automatically what will happen? I will read the 4 bytes from the starting from one address, address plus 1, address plus 2, address plus 3. Let's say the processor generates an address 0. Then the moment it generates an address, I will read what? 0 also, I'll read 1 also, I'll read 2 also, I'll read 3 also. Then how much of data I'll get? I will get data of 32 bits. Because why? Each bank contributes 8 plus 8 plus 8 bit, 32 bit, then I'll read it. So that is why memories are organized as words, even though memories are byte addressable. So this concept you should be able to understand. Am I audible?
Yes, sir.
Okay. So now we will organize the same processor and the memory with a little difference, Now I'll organize the memory as a words. So I will organize the memory as a words. So one location, one address is nothing but a one word. If, for example, if it's a 32 bit, for all practical reasons, we will take 32 bit as a word length. So each word consists of 4 byte addressable locations are there. The first word starts at 0. The second word starts at what? 4. Because why? 0, 1, 2, 3. Then the 4 starts. Then the next address will start at 8. It continues like that. Then you will have the last word will be available here. So now onwards, I use a word called as word addressable memory. So memory or allocated or organized as a words. How do we get this word organization? By using a banking concept, we'll get this one. Now, apart from these, now when you organize the memory as a words, you can able to read 4 bytes at a time or 32 bits at a time from the memory into the processor. So let us take one important consideration. So before we proceed further, let us take a 32-bit number. 32-bit number. We will see that how it is stored inside the memory. Now the number 0x11223344. Some number I have taken it. And this 0x means we know that in C language it's an hexadecimal. So I have represented this number hexadecimal. Now I want to store this number in the memory so that I can use the data whenever required in the program. Now, how do I store this data in a memory location? Let us take one word, first word. I want to store in a first word this data. Now, I can store this data into the first word of the memory location in 2 ways. So for example, if you look at this, this consists of 1, 2, 3, 4, 5, 6, 7, 8 digits are there. Every digit represents what? 4 bits. That means that 4 into 8, totally 32 bits are there. So that means that every 2 digits is 1 8 bits, next 8 bits, 8 bits, there's totally 32 bits are there. Now, so we know that every word consists of 4 bytes. That means that this is 8 bits, this is another 8 bits, 8 bits, 8 bits here. So I can store either 44 into any one of these locations because 44 is what 8 bits and every address which is associated with the first word is also, it is also referred as 1 byte. So now two possibilities are there. I can start writing the 44. I can start writing the 44 from this address. 44 I can start. 33 I can start writing like this. 22, 11 I can write it. Or I can write the same thing as 11, 22, 33 and the 44 I can write it. So that means that the moment you put this data into a memory, that means that there are instructions are there, what is called define word. So if I say location 1, define word, so 0x, 11, 22, 33, 44. This is the statement what is provided in assembly language. It's called as an assembler directive. So like this, if I give in as a for an assembler, what does it does? It identifies the memory address of the location 1. In this case, I've taken a address is 0. So, and there you should able to store this number into the memory location. That means that whenever you give this type of statement in assembler, it takes this number and store either in this format and this format. So you should know as a programmer which format it store, so that then only you can able to manipulate this data whenever you want to extract this data in 1 or 2 bytes of the 4 words you want to, 4 bytes you want to extract. Only if you know this, you will be knowing that you are able to extract the data, required data out of the 32-bit number. Now, if let's assume that how it is stored. If this is the LSB, this is the lower significant byte of a number. This is the most significant byte of a number. So totally 32-bit number is there. The first byte from the right hand side is LSB. The 11 from the left hand side is called the most significant byte. Here from address also we'll find out. So what is an address of the first location? Let's say address of this is what? So 0, address of this is what? 1, address of this 2, and address of this 3. So that means that I know the addresses of each of these locations. I know which is LSB and which is MSB. Let us observe in this case, first case. Now here I am storing the 44 in the address 3. So the 44 is stored. Look at here, the 44 here in this case is stored in address 0. So there is a rule is there. If lower significant data or lower significant bytes or lower significant data is stored in the lower address, this technique is very popularly called, this type of representing the data in the memory, they are popularly called as Little Endian format. So this is the popular format followed by all Intel processors. If you make this declaration in Intel processor like an 8086, so you will get the data in this format. So what is the rule? If you take any 32-bit number, the lower significant, least significant, the byte will be stored in the lower address. Which is the lower address among the 0, 1, 2, 3? 0 is the lower address. So that 44 will be stored here. So what is the next address? 32. So what is the next address here? Here. If you look at 11, the most significant byte, it will be stored in the highest address of the first word associated with the 0 address. So 3 it will be stored. Here if you look at that, the lower significant byte will be stored in the higher address. For example, address is 3. So 44 is stored. Here most significant byte will be stored in the lower address. So this type of is called as Big Endian format. Big Endian format. So any Motorola processor, if you take a Motorola processor, all Motorola processor follow this formula. If you take any Intel processor, they follow Little Endian format. So the same statement, if you compile and just observe the memory contents by using the dump command in a debugger, you can just find out there is a difference between the way it's represented in the memory. There are certain processors called as ARM processors where the facility is provided either I can represent in the Little Endian format or in the Big Endian format. By default, it will go to the Little Endian format, but there is a configuration is there in the ARM processor. By configuring certain bits, I can make it to work as a Little Endian or a Big Endian format is available. So let's solve one small quiz question now. So now we'll solve one small quiz question. So give the contents of, or mention the contents of memory, So starting from 2000 for the 32-bit number, so let's say 0x 18 34 76 00. So using Little Endian format. So now, if I ask a question like that, immediately I should know that 32-bit number means how many addresses are required? 4 addresses are required. Instead of writing them as a one word in a horizontal row, now what I'll make it? I will just write them as 4 locations like this. Now address is what? 0, 1 instead of 0. So they have given the address as what? 2000. So then 2002 and 2003. There are 3 addresses are available now here. So this refers to the first location and a third location. Now, what is my data? This data. I want to store them. I want to know that how it's represented in memory. The whole of this refers what? One word, 132-bit number. So now, since it's a Little Endian format, lowest significant byte is what? 00. So I'll copy 00. The next byte is what? 76. I'll write here. Next is 34. I'll write the 34 here. Next is 18. I'll write the 18 here. That means that given any 32-bit number, if I know the starting address of my word, I can able to clearly allocate each byte where exactly sits in the 4 bytes associated with the one word. So this is a fundamental requirement before you start assembly language program, because unless we know where it's allocated, how it's stored, we cannot write the programs. Okay, so now we have understood how to represent the data in the memory. We also understood that what are the lines are required to communicate the processor to the memory. One is an address lines, other is a data lines. There are other set of lines called as a read and write signals are available, which indicates whether I'm writing the data to the memory or I'm reading from the memory. That we will see later when we design the processor. So now we will start with this knowledge, we will start writing the program now. So when we start writing the program, now the instruction, whatever I'm going to write now for writing my programs, every instruction, whatever we write in ALP language consists of certain operands in the instruction. For example, if I take add instruction, so I can just write some number #20 and location. So what does it mean that? So that means that I'm adding number 20 to the memory location called location. The name of the location is called LOC, which is in the memory. So I'm storing the answer back into the location. So I'll just give 1 or 2 like this, and then we will able to understand how does it works. So if I write like this R0, R1 and only 2 operands, that means that I am adding the contents of R0 to the R1. I'm storing the answer back to the R1. If I write only one operand add A, that means that adding the contents of memory location A to some other implied place, and answer is stored at the implied place. So that means that we will be writing instructions like this. Before we start writing the instructions like this, let us put a first question to ourselves. Now, what is the question? If I write any instruction, now instruction require what is called as an operands. The operands can stay in 2 places. Operands can exist either in the registers of a memory, or operands can be there in the memory location. There are no other places available. You take any processor, just look at this processor, see that either you should have the data inside the processor registers or should have the data inside the memory. No other place is available. So whenever I write any instruction in assembly language, the operands which holds the data either should exist in the registers or should exist in the memory. Now, what is the challenge of specifying operands in the memory? So let us take an example of one instruction. Let's say add now A, B and C. Now take an example of this case. We will find out what is the challenge available here. I want to add the contents of these 2 locations A, B and store the answer into the C location. That means that, so the moment I look at instruction, I can understand whether my operand is located either in the memory location or register. Look at this instruction. If I ask you the question, where is my data? You can immediately say the data is in the processor. Because why? I use the registers. If I ask this question, where is my data? You can immediately tell, sir, the data is there in the memory because I used some name for a memory location. And the number is also stored as a part of the memory. If I ask this question, where is my data? One of the operand is in the memory location, other one is implied place. Implied is inside the processor always. So that means that by looking at instruction, you can able to tell where is my operand is located? Either it's inside the processor or inside the memory location. Now, when we have number of operands are located in the memory, there is a challenge is available. So what is the challenge? If I convert this instruction into a machine language, we will convert into a particular size. If I'm able to convert this instruction into 32 bits, what is an advantage for me? I can able to store the complete 32 bits, that is one instruction, into the one memory location. So if you look at this here, if I'm able to write one instruction in 32 bits, one instruction can fit into the one word of a memory. If I'm able to do not able to fit the instruction into one word, then what do I require? Then I require a multiple words. So one word, second word, and the third word also required, the fourth word. How many words are there here? Now 4 words are there. How many words are there here? 1 word is there. That means that any instruction I write it, sometimes the instruction will take 1 word, 2 word, 3 word, or sometimes it take 4 words also. How we can able to say that it is taking 1 word or it's taking a 4 word? It depends upon the way you specify the operands. Now let's understand now. Let's take now example. In this example, we are understanding that we are writing a program So now I'm just telling that. So I've just written into other one. Okay, the instruction which occupies sometimes 4 words also. So it occupies 4 words also. Sometimes the 1 word also. So that means that sometimes 1 word, 2 word, 3 word, or 4 word, it occupies it. How do we know that whether instruction requires 1 word, 2 word, 3 word, 4 word? It depends upon the how you specify the operands. If the operand size depends upon the memory location. Now, so if I say that the operand A is a memory location, it is a memory location. So that means that I should able to indicate the address of that memory location. Then let's say A is there in the memory location now. So A memory location means, it means that it is indicating one of the address in the so many locations, whatever available words. So now this address is associated with the symbol A or the name A will contain certain address bits will be available. How many address bits will be required? It depends upon the address bus. If the address bus of the memory is 32 bits, that means that A will be represented in 32 bits. So let's say the address of the A is 2000. 2000 is the address of the memory location. Now 32 bits, that means that 2000 I should be able to represent 0000000. Correct. Now whatever the value I'll get it 1000 something. That means that this 2000 I am writing inside this 32 bits. Because why I require 32 bits? You may tell that 2000 is a small number. I don't require 32 bits. But this address can vary from 0 to any 32 bit number. So starting from 0, I can go to any address. That means that always 32 bits are required to represent one address if the processor address capability is what? 32 bits. So that means that if I write an instruction called add ABC, what does it mean? That when I convert into machine language format to specify the 32 bits, 132 bits, I required what? One word is Hello? Hello? Am I audible?
Yes, sir. Audible, sir.
So one word I can represent A. Similarly, to represent B, I required another word. B is required. To represent again C, I require another word is required. Next, one more word I require for what is called representing the meaning of the add instruction. That is called opcode for some other information. That means that 4 words are required. Whenever you require more words are required for one instruction, the time you require to fetch that program, that instruction from the memory is what? It will be more. For example, let's say 1 clock cycle is required to fetch 1 word from the memory. Now, since your program consists of 1, 2, 3, 4 words are there, now the processor requires 4 clock cycles to fetch 1 instruction. So that means the time is it consumes more amount of time to execute your task. So that is why generally the tendency is what? We were able to put all our instructions, majority of the instructions in registers and less amount of operands. if I write the program like this, let's say add AB. In this case, what will happen? I am able to represent two operands, only two operands, A one operand, B one operand. When I add these two operands, I'll get the answer. Assume that answer is stored in the B itself. That means that if I make an assumption like that, contents of A, contents of B is added. If I store the answer back into the B, now the advantage with this is what? You require only 3 words to represent this instruction. Because why? To represent A, to represent B, and for the add. So if I write an instruction only with a small, like a R0, R1, R2, in this case, the amount of memory what is required to represent instruction is very less. Because why? How many bits are required to represent any register? For example, you have 32-bit registers are there. If 32 registers are there, so 32 registers mean 2 to the power of 5. So 2 to the power of 5 means 32 different registers I can able to represent. If I assume there are 32 registers are there, and 32 means 2 to the power of 5, 32 different registers are there. 5 bits are required to represent one register. That means that 5 bits are required to represent R2, 5 bits are required to represent R1, 5 bits are required to represent R0. And that means that whole of this instruction I can able to put it what? 132 bits I can able to put it. Now what is an advantage of this instruction? That means that I can able to execute the one instruction by one clock cycle. Because why? The whole of the instruction I can put in one word. So if I get one word into the process, I can finish execution. Whereas if I put lot of memory operands in the instruction, then what will happen? So you require number of words will increase. So based on the number of memory operands you specify in the instruction, instructions are classified into 3 types. So we will understand. This is a very common question generally asked. So we will understand what other types are available. Now, so based on the number of instructions, based on the number of memory operands available in the instruction, we will classify them into 3 types. So I'm just calling them as instruction types based on the number of operands, number of memory operands in the instruction. So what are the classification? These are generally available. Most of the process will follow into one of these category. The first one. So the first one type is called as 3 address instructions. 3 address instruction. So example is what? Since we have already seen that 3 address means I will explicitly specify all the 3 operands which are required to perform an instruction execution. So what will happen in this instruction? The contents of A added to the contents of B, and the answer is stored into the C register. These 2 operands are called as source operands, because which will contribute the 2 operands, and this is called as destination operand. So when do we call 3 address instruction? If I am able to refer 3 memory location in a single instruction, so that I have the flexibility of using the 3 addresses directly. I can add any 2 memory locations and store the answer in any one memory location. That type of instruction is called 3 address instruction. What is the disadvantage here? Size of the instruction is more. It requires around at least 4 words to represent your instructions. Since it consumes more space, many processors have designed 2 address instructions. So 2 address instructions. We will take an example for that. So example for 2 address instruction is add AB. In this case, the one operand, that is what is called as destination operand, is what is called implied. Here one operand. So one operand, that is generally we call as a destination operand, is implied. So implied in the sense we don't specify them in instruction, but the instruction knows what is the destination. How does it makes an assumption? Because it thinks that one of the source operand will act also destination. That means that, so one of the source operand acts as destination operand here. So even though we don't specify, it's implied. So one of the source operand, that's the second source operand, is consider as also destination operand. I can write this instruction meaning of that. Add A plus, so add A, so plus the B, and the answer is stored into the B itself. This is the meaning. What is an advantage of a two address instruction? It is better than the first one because the number of words required to represent the instruction memory is less. Most of the processors will follow this type. So now third one, there's another instructions, there's another type of process available which will reduce little more. It's called as single address instruction, single address instruction. Most of the ARM processors will follow this format, single address instruction. How does this instruction will perform the same job? So I am adding A. I use the instruction called A. Now, what is the meaning of this instruction it carries here? A is added with, so what is with? Here, one source operand and destination operand is implied in the sense, so when you write that instruction, processor understand that one of the source operand is present in a particular and the answer is also be stored in a particular place. So what is that? The place? Generally, it is called by a popular name as accumulator. So in most of the processors, earlier processor, they call it accumulator. So what is the meaning of accumulator? Accumulator is also called as implied destination. It's also called implied source operand. That means that when I use this instruction, one of the operand is specified by A plus accumulator, and then the answer is stored in the accumulator. So in a single address instruction, always remember that there is an implied place is there for holding one of the operand, and also there's an implied place is there to specify the destination. Generally, accumulator is a name we use for that register which is present inside most of the processor. For example, in Intel processor, we will call the accumulator by the register name called AX. So if it's an 8-bit, you are performing AL. So AL or AX is an accumulator in case of Intel processors. So accumulator serves as a place for holding the source operand and destination operand. It's a single address instruction. Advantage of single address instruction is most of the single address instructions may require 1 to 2 words in the memory, so that compared to the 2 address and 3 address, the space required in single address instruction will be very less. So now most of the process will also specify, other than the accumulator, there is a general purpose register also you can able to use it. So for example, in ARM, you don't require to use an accumulator. You can use other registers also along with the single address instructions. We will see that example later. Now what we'll do is first, now we have understood 3 address, 2 address, single address instruction. So one question we will solve it, exam question last year. So write a program, write the program using 3, 2, 1 address instructions to implement following logic. So what is the logic? So now C is equal to A plus B. Let's say high level language statement. I want to write this program using 3 processor types. Let's say now we will write the processor, we'll write the instructions for this statement using 3 address instructions, now. How do we do it? It's a single line statement here. So what is an instruction here? It's directly, I can write it, add A plus B, C. It's finished. One line is sufficient to write the program for this one. That is an advantage of what is called 3 address instruction. Somebody asks, of course, there is a disadvantage with the 3 address instruction. Many words are required. But what is the advantage? It's very easy for the programmers to implement complex logic because you can directly specify the memory operands of your interest and start writing the code. So it's number of instructions which are required to write the logic for a particular task is less. Whereas as you move from 2 address to single address, number of instructions required will be more. So now let's write for a 2 address instruction. Now same program, let's write for 2 address instruction now. Now what is the logic required for this? Now for a 2 address instruction, now I can only specify only 2 operands in the instruction. So what I will do is, now I'll move the contents of B to the C register first, move. So what is a move instruction? Move, MOV or move, you can write anything. So I'm moving the contents of B to the C. So that means that the contents of B location is moved into the C location. So C contents is overwritten. Anyway, I require to store my answer in the C. So that is why I am moving one of the operand, that let's say the B, I am moving into C. Then after that, I'll perform add operation. Add. So what is the other number? A. Since already one number is moved into C, I say AC. Now what does it mean? That the contents of C will be added with the contents of A and the answer is stored into the C register. Because we know that in 2 address instruction, the destination is nothing but what? One of the source operand. So A plus C and the answer is stored into the C. So that means that in this case, 2 instructions required to perform a job. Here one instruction required. Let's write the other one. So for a single address instruction, one address instruction. Now what is the program for this one? I said you require to depend on accumulator which is present inside the processor for holding one of the operand, and also you should think that answer is always stored back into the accumulator itself. Now I will be requiring certain instructions now. So move instruction is also sometimes we use what is called load. Whenever we bring the data from memory to the processor, sometimes we use the word called load. Whenever I want to store the data from processor to the memory, I will use a word called store. So I bring the data from memory to the processor means load. From the processor to the memory means store, I will be using it. So in some processor, they use a move instruction. Some processors, they use a load and store. So here I use a load and store so that we can appreciate the load and store instructions also in the programs. Now first, I will get the first number into the processor accumulator. When I say load A, that means that the data what is present in the memory location A will come to the accumulator. So A contents will move to the accumulator, move to the accumulator. Now one number is available now here. Now what I will do is I can perform one operand, add B I specify. When I say add B, what does it do? One of the operand it assumes in accumulator because already accumulator contains first operand. So accumulator is added to the contents of memory location B and automatically the answer is stored into the accumulator. Now I done the addition. Where is my answer? Answer is an accumulator. Now I'll store. So store C I will do it. So when I say store C, what does it mean? That the contents what is present in the accumulator will move to the memory location called as C. So here in this program, instead of load, I can use move also. Here instead of store, here I can use move also. But sometimes some processors will use a load and store. So in Intel processor, there is no word called load and store. They use everything move for moving the data within the registers, moving the data from memory to register, they use a move. But ARM processors, whenever the memory is referenced, they use a load and store. Whenever you are moving the data within the ARM processor among the registers, they use a move instruction. So don't worry, whichever you feel comfortable, you can use that one. So summarizing for a one address instruction, first we got one of the number into the accumulator. Then we added the number what is present in the B register to the accumulator. Then answer what is there in the accumulator. It's stored back into the C register. Look at how many instructions are required. There are 3 instructions required. As we move from 3 address to the 1 address, number of instructions required will be more and the program writing is complex. You found that when I write a program in a single address instruction, it was a challenging for me. I have to think about the logic. Whereas in case of a 3 address instruction, program writing is very simple. In a single statement, I could able to write it. That means that the logic development will be difficult for a programmer, but the number of words what occupies or the total size of the program will be very less when you go for a single address instruction. Most of the ARM processor will go for a single address instruction, whereas most of the Intel processor can go up to the 2 address or 1 address instructions also. So let's now go to the next topic. Any doubt? You can just. So I will stop the video and then record again.